Hey guys, let's talk about solutions to linear difference equations when I spell linear wrong. So, what's a linear difference equation? Well, it's the same thing as a linear differential equation, just with k plus 1 instead of the differential, right? So, we're going to consider, in this case, the difference equation as being given by x, k plus 1, where x can be an n-dimensional term, is equal to a matrix. So this is a time-varying matrix where time is based on k now, right, instead of t, times x of k plus f of k. Okay, so our f of k is our input. Or forcing function input. Our x is our state, and this will be in our n, and that's our state. This is our system matrix here, A. Let's say system matrix. And this will be in Rn cross Rn. And K, again, is our time parameter, right? So this will be our time parameter. And this is in our natural numbers, right? Which again is defined as 0, 1, 2, all the way up. Pretty cool. All right. So how do we talk about solutions to this? Well, first, let's look at what happens as we solve this out by just recursively going through the process and looking at what the results are. Note that we need an initial condition, x naught is equal, x at time 0 is equal to x naught. So this is the initial condition there. All right, and so let's recursively solve, look at this over time. Over k, okay? So let's look at the case where k is equal to, first let's equal to 0, right? This will just be, this will imply that we have x of 0 plus 1, which is equal to, which is k, right? So this will give us x at 1. This will be equal to a at time 0 plus times x at time 0 plus the function at time 0. All right, so that's pretty straightforward. Next, let's look at the time where k is equal to 1. So the next time step, this will be x at 2, right, is equal to a at time 1, x at time 1, plus f at time 1, right? So now we have x at time 1. That's from the previous step here. So then this will open up to a of 1 times the sum of a at time 0, x, the initial condition, plus f at time 0, plus f at time 1, okay? So now this will be equal to a1 times a naught plus, oops, and then I need the initial condition in there, plus a1 times f naught plus f1. All right, so that's what it is when k is equal to 1. See, when k is equal to 2, we'll get, result will be equal to x at time 3. This will be equal to, again, just plugging it in here, and then recognizing that x at time 2 is exactly from above. So then this will lead to a2 times a1, a naught. Yeah, I'll feed you in a little bit. Plus A2 times A at 1 times F naught plus A2 times F1 plus F at times 2, at time 2. Okay? And then this continues. So, but you can already start seeing a relationship here. Do we get it again? Come on, update. Okay, great. So you can see, you can start seeing a relationship here. We get basically at every time index, we're multiplying by the system matrix at that time by all previous system matrices, and then we're also applying those system matrices, each one to all previous forcing functions, right, up until the most recent time. Okay, so so this continues. So I'll just put some ellipses here. So then it follows. It follows that in general, we can write this as just a closed system of x of k is equal to ak times ak minus 1 times all the way out till a at time 1 times the initial a times the initial condition plus the sum k minus 2 tau is equal to 0 of k of a times k minus 1 a times k minus 2 a times of tau plus 1 times f of tau plus f of k minus 1. Okay, so this guy here, this second term here is all one term. This is one term, and then this is one term. All right, so if you were to look at this in terms of differential equations, this would be our homogeneous solution here, and this would be our particular solution, right? So this would be the solution that's forced, and then this would be our natural solution, right? So we can, just like with continuous time systems, we can consider this notation right as phi of k and tau, which is equal to a k minus 1, a k minus 2, all the way out to a tau plus 1 times a tau. Okay? Then we get that our solution at time k is equal to phi k and 0 x naught. Oh, you act like you're dying. You're fine. Phi of k and tau plus 1 times the forcing function at time tau. Down. You're embarrassing me. This will be taken from tau is equal to 0 to k minus 1. Great. So as you can naturally see, we're going to call this phi, got a guess? State transition matrix. That's right. Worlds apart, right? All right. And then when we can, if we're taking the forcing function as 0, so if f of tau is equal to, or f of k, let's say, is equivalently equal to 0 for all k, then what do we get? We get that x of k is equal to just this, just the state transition matrix times our initial condition. Just that easy. All right, now let's look at an example for this one. All right, for this example, let's consider x of k plus 1 is equal to k plus 1 squared x of k plus 1. All right, with an initial condition, x naught is equal to 1. Okay, so first note that in this case, we just have n equal to 1, so we have just a first order difference equation. So n is equal to 1, which is a first order difference equation. So again, this means that that each next step is only dependent on the last step. It's not dependent on any more steps beyond that. Okay, now putting this system into the notation that I just defined, we can get the following. We can say that our a of k is just equal to k plus 1 squared. We can say that our forcing function f is just equal to 1. Okay, so then our state transition matrix, which I defined on the last page again. Again, the state transition matrix is equal to this guy. It's just the product of each of the state transition or the state matrix at each time step, right? Between k and tau. Okay, so now in this case, we get that this is equal to k squared, k minus 1 squared, all the way out to tau plus 1 squared. Okay. Turns out that this is equivalently equal to k factorial over tau factorial squared. Pretty neat. All right. So knowing that the state transition matrix is k factorial over tau factorial squared, we get that our solution, which is equal to, again, it's equal to the state transition matrix from 0 to k times the initial condition plus the sum. Let me just remind myself over here. Oh, I have it written here. What am I doing? The sum of, move that there, k tau plus 1 times the forcing function tau equal to 0, from 0 to k minus 1. All right. So now plugging in what we have gives us k factorial over 0 factorial squared times 1, which is, again, the initial condition, plus the sum of k minus 1 of tau equals 0 to k minus 1 This will be k factorial over tau plus 1 factorial, and then this whole quantity squared times 1, which is the definition of the forcing function for all time. All right, so then this guy will be equal to k factorial, oops, I hate when it does that, squared plus, if we pull out this k factorial, it's not dependent on tau, right? So we can pull that out front. This will be k factorial squared out front times the sum of 1 over tau plus 1 factorial squared. Sure, something really fast. Okay. All right, and so then this guy, turns out, is equal to k factorial squared plus, or times rather, times the sum of 1 over tau factorial squared from tau is equal to 0 to k minus 1. Okay, so basically we recognize that this guy right here encompasses the point at tau minus 1 value. So that makes up for the denominator there. Let me rewrite, make sure that this is tau is equal to 0 to k minus 1. Right, and so now this guy, at the end of the day, we get our solution to our difference equation is equal to k factorial squared 1 over tau factorial, tau equals 0, k minus 1. And then this guy is our full solution. So now we can say that give me a k, I can give you your x for any value of k instead of iteratively going through. Say I wanted to find k at 2 million, right? So one thing you could do is you can solve this x at k of k plus 1 equal to k plus 1 squared times x of k plus 1. You could solve that out 2 million times to get me x at the index 2 million. Or you could just plug it into this this equation down here at the bottom and have it immediately by only calculating a couple values. You'd have to do 2 million summations, but that's better than having to do this multiplication 2 million times. That's all I got for this lecture. Next, we'll go over something else.